So for today's lesson, what we're going to do is the second day of transformations, and we're talking about rotations and dilations. A rotation is a transformation in which a figure is turned around a point, and this point tends to be called the point of rotation. In the coordinate plane, this point is typically the origin. So rotations can be counterclockwise or clockwise. You basically follow the quadrant system. So in the quadrant system, where this is 1, this is 2, this is 3, this is 4, you tend to go around this way. That's why if it's counterclockwise, following the quadrant system, counterclockwise are considered to be a positive rotation, and then clockwise are considered to be a negative rotation. All right? So then when we talk about something that is rotational symmetry, you've got rotational symmetry if basically when you can be turned about a point and you end up becoming your own point again, where you've gone more than 0 degrees but less than 360 degrees, you have rotational symmetry. Rotational symmetry of exactly 180 degrees is considered to be point symmetry. So point symmetry basically says that if I can turn a figure just exactly 180 degrees, if that figure is itself, then I've got what's called point symmetry. So if we talk about point symmetry for these groups of letters, and I'll bear with me for a second, if I turn these things all the way upside down, the letters that remain themselves, that mapped onto themselves, for example, Z is still a Z, S is still an S, O is still an O, N is still an N, I is still an I, H is still an H, and that's it. Those guys happen to have point symmetry. I happen to miss one, I apologize. Whoops. I happen to miss letter X also having point symmetry. So point symmetry is exactly 180 degrees. I'm going to turn this thing around again. The things won't really match up, but if I go back around again, okay, so let's kind of fix this. So let's get those letters again that we need. So which letters have point symmetry? The exactly 180. We'll do this again. We've got the H, the I, the N, the O, the S, the X, and the Z. All rotations are always going to be counterclockwise, following the quadrant system, unless otherwise stated. So always around the origin, always counterclockwise. The rotation mapping rules go like this. If you start with a point XY, when you rotate 90 degrees in that coordinate grid, and let's kind of show you this real fast. In the first quadrant, everything is positive. In the second quadrant, your X's are negative, your Y is positive. In the third quadrant, they're both negative. And in the fourth quadrant, you've got a positive and a negative. So as you do your rotating and you go from quadrant 1, where XY is, when you've got a point in quadrant 1 and you rotate it 90 degrees, counterclockwise as always, what's happening is you're going to switch your coordinates and you're going to change the sign of the first. So it becomes a negative Y with the positive X. And then if you go again from there, you're going to switch your order and change the sign of the first. Then it becomes negative X, negative Y. And if you flip and switch again, it becomes Y, then to negative X. And if you switch and change again, you get back to where you started. Okay, so the way to sort of memorize the mapping rules is you're always going to switch and negate the first. So switch, then negate the first. Okay, so if we take the point -2, 3 and we rotate this thing 90 degrees, we're going to switch the values, but we're going to negate the first. And then if we go about 180 degrees, let me try that again. And then if we go 180 degrees, we're going to switch, but we're going to negate the first. That becomes +2, -3. And if we go again to 270, we're going to switch, but we're going to negate the first, and that becomes a positive 3 and a positive 2. And then if we go one more time, full circle, we're going to switch, but we're going to negate the first. Okay, and that gets you back up to where we started. So 360 degrees is going to be back mapped onto itself. Okay, so you're switching and you're negating the first. With dilations, that's where things get bigger or smaller for that matter. So a dilation is a transformation when the size of a figure is changed, is enlarged or reduced, and the figure is moved. Dilations have a constant, I guess we'll have what's called a scale factor, and the scale factor happens to be the letter K. If you remember from last year, scale factors are things that you would multiply by. So you multiply both x and y by the scale factor, which is k. So if you want to find the coordinates of 2, -4 under dilation of -2, you're going to take your coordinates 2, -4. You're going to multiply them both by -2, and you're going to turn out to be at the ordered pair that becomes -4, +8. You don't really have to show any work. You can just do it. This one says find the constant scale factor that maps -4, 6 onto -10, 15. Well, basically you're saying to yourself, if I multiply -4 by some sort of scale factor and I end up at -10, what's my scale factor? Divide both sides by 4, and the k, if you simplify it, becomes 5/2. If you want to make that 2.5, so be it. Last example. You've got triangle EAT. What's the image of EAT under dilation of 1/3? You're going to graph the original and its image, and you're going to state the order pairs of the image. So if I take E, 3, -3, and then A, 3, 12. Kind of hard to fit that one in there. It's off the graph a little bit. And then I take T, -9, 3. And I connect the dots. Well, if I want to find my new EAT, which is going to be E prime, A prime, T prime, and I dilate by 1/3, all you're doing is really dividing everything by 3. So the new coordinates of E prime would be 3 divided by 3, -3 divided by 3. A prime, 3 divided by 3, 12 divided by 3. T prime, -9 divided by 3, and 3 divided by 3. And so now you've got this new triangle, 1, -1, E prime, 1, 4, A prime, -3, 1, T prime, that's 1/3 of the size of the original. And that's it.